Information. Obvious goal in predictive modeling is to extract information from a data set. Probability revisited. Relative frequency in simulation, joint probability and its interpretation, but the ultimate goal is information. Before we can get to information, let's do some review. Big data is not necessarily random, nor does it need to contain randomness. However, it can be random, at least in part, and some randomness is typical, and concepts from probability and information theory are important regardless. So let's look at probability, especially with multiple variables, and there are more examples in the additional videos. Variables associated with a process. The sample space of a process is the set of all possible outcomes of that process. A variable x is associated with a process or with its sample space if in any trial of the process the value of the variable is in the sample space. A random variable is simply associated with a random process. So for instance, if we have s as heads or tails, then we know that if x is associated with s, then x is either a heads or a tails. If x is associated with the sample space s equals 1, 0, then x is either 1 or x is either 0. A random variable is just a variable. The word random simply refers to how the variable obtains its values. Now, if we have a sample space, we usually index the outcomes, O sub 1 up to O sub j up to O sub capital M. The probability of a random variable x being assigned an outcome O sub j is written probability of x equals O sub j, or the probability of x equals j, or just p sub j. For example, if we toss a fair coin so that the s is tails or heads, which corresponds to outcomes O sub 0 and O sub 1 respectively, then the probability that x is a heads is the same as saying the probability that x is equal to the event O sub 1, which we will often write just the probability that x is the outcome corresponding to 1, or p sub 1, and in all cases that's a half. The properties of probabilities. The probability that x equals O sub j is non-negative for all j equals 1 up to m. The sum of the probabilities is equal to 1, the sum over all outcomes. Or equivalently, p sub 1 plus up to p sub j plus up to p sub capital M is 1. And we will often use x, lowercase x, instead of j as an index. So if we have a capital X associated with some sample space S, which is O1 up to O sub lowercase x up to O sub m, capital M, then we'll often write the probability that capital X is the outcome O sub x simply as P of x. So for example, the sum of the probabilities over all outcomes is 1 would be P of 1 plus up to P of x plus up to P of m is equal to 1. Now let's suppose that x is associated with a random process that has a sample space S, and we're only going to look at finite sample spaces for now. We're going to generate n trials, and n here is going to be very large. And then we're going to draw a bar chart for each outcome O sub x. The area of each bar is the ratio C sub n of O sub x to n, where C sub n of O sub x is a count of the number of times that O sub x occurs in n trials. So we'll get this graph with all these bars, and the area of the bar is a relative frequency, and often we'll index the axis by just the indices. So we'll use x instead of O sub x to refer to the O sub x outcome associated bar. We're going to assume independence of trials, so the next trial, the n plus first trial, could produce any outcome for x. But we can predict its average, or predicting the average is what's going to be called the expected value. So, and that predicted average is different from an actual average in that we're letting n go to infinity. N's arbitrarily large. So the expected value of capital X is E of the quantity capital X is the limit as n goes to infinity of the average of the x sub i's. Now notice that the outcome indexed by lowercase x occurs C sub n O sub x times, so let's rewrite the expected value. Now first we'll notice that the probability P of x, which is the probability of outcome O sub x occurring, is the limit as n goes to infinity of the average of the counts, C sub n of O sub x. And that's actually the relative frequency as n goes to infinity. Now let's look at the expected value E of x. What we're going to do is we're going to take all the indices that we get in I equals 1 up to n trials, and we're going to group them. So I sub x sub 1 up to I sub x sub r will be those indices occurring to trials in which outcome O sub x occurs. So here's our expected value, and we've rearranged. These are all the same indices, so the indices all go from 1 to n, but we've rearranged so that the first however many group are all equal to 1, and so on up to the x sub I sub x1 plus up to plus x sub I sub x sub r. Those are all trials in which the capital X sub I was equal to a lowercase x, or the outcome associated with it, and then finally all that are associated to m. So that means that first group is just 1 times C sub n of O sub 1 over n. The group corresponding to the index x is x C sub n of O sub x over n, and all the way up to summing the m C sub n of O sub m over n. And that's just 1 times the probability of 1 up to x times the probability of x summed up to m times the probability of m. In other words, the expected value of x is the sum x equals 1 to capital M of x p of x. Now notice that's actually the same, because of the way we define the area of the bars, as the integral from negative infinity to infinity of x p sub x, or chi p sub chi d chi, because we actually were working with areas when we were working with those relative frequencies. So an expectation is a predicted value as n goes to infinity. So the relative frequency is C sub n O sub x over n. That's over n trials. So the expected value of the relative frequency is what we call the probability. So the average x1 up to xn over n, that's the average of x over n trials. Its expected value is E of x, which is the limit as n goes to infinity, 1 over n sum I equals 1 to n of x sub I, which is just the sum x equals 1 to capital M of x p of x. Now suppose we have a function defined for all index values. Then f of the quantity capital X sub 1 summed up to f of the quantity capital X sub n over n, that's the average value of f of capital X over n trials. So what is the expected value of the average of f of capital X over n trials? It's E of f of capital X is equal to the sum x equals 1 to m f of x times p of x. That's not a derivation, but you could actually rederive it the same way we did just for E of x. Now let's look at two variables. What kind of experiments can you have with two variables? Well, you can roll two dice simultaneously. Capital X the outcome of the first, capital Y the outcome of the second. A square on a chessboard could be chosen at random from row X and column Y. You could choose two cards from a deck of cards. X is the first and Y is the second. You could take the first and last names of a person selected at random. Capital X would be the first and capital Y would be the second. Now the notation is slightly different because for each outcome we have to have two indices. So our S would be the set of all outcomes O sub I j, where I goes from 1 up to capital M sub x and j goes from 1 up to capital M sub y. And then the probability that capital X is equal to I, capital Y equals J, that's just the probability that outcome O sub ij occurs. We often use lowercase x and y in place of I and j. So S, the sample space, is set of all outcomes O sub x, y, and the probability that capital X is lowercase x, capital Y is lowercase y is just the probability that outcome O of x, y occurs. Simultaneous variables. So we call the probability capital X equals lowercase x, capital Y equals lowercase y, which we often write as P of xy, joint probability. And it is the probability that capital X takes on the value little x, capital Y takes on the value little y, in the same trial. So let's look at an example for the notation. Suppose we have 100 students allotted randomly among 4 teachers. A trial would be a teacher and a student selected at random. Capital X corresponds to student, capital Y to the teacher. So M sub x is 100, M sub y is 4. So our sample space is O sub xy, where x goes from 1 up to 100 and y goes from 1 up to 4. So we have outcomes. O sub xy means the outcome of student x put with teacher y. And the probability that capital X is little x and capital Y is little y is the probability of a student number x being allotted to teacher number y. Let's look at an example. So let's suppose that Dr. Yu is in China and I am in the United States, and we both flip fair coins. So x is my outcome, y is U outcome. So the sample space is tails, tails, heads, tails, tails, heads, or heads, heads. That's little o sub 00, little o sub 10, little o of 01, little o of 11. So a trial, for instance, could be capital X as a heads and capital Y as a tails. So I got a heads and you got a tails. Each outcome's equally likely, so the probability, for instance, of this o sub 10 is a fourth. Or in function notation, p of 1 comma 0 is a fourth. Now, marginal probabilities are probabilities of individual variables constructed from joint probabilities. So the marginal probability p of capital X as a function of the index x is the sum, y equals 1 up to capital M sub y, of p of x comma y. And likewise, p sub capital Y of little y is the sum, x equals 1 up to M sub x, p of x comma y. So the marginals are the probabilities of individual values of x and y respectively given a joint probability. And often we'll just write p of x and p of y if there's no confusion. For example, let's look at 2 fair coins. So x is the outcome of my coin, y is the outcome of U's coin. The sample space is the 4 possible combinations. So the marginal probability for me, p sub capital X of 0, is the sum over the y's. And so this is the probability that my coin is tails, is the sum over the y's. And where M sub y is 1, and so y is going to go from 0 up to 1. And that's p of 0 comma 0 plus p of 0 comma 1. And that's a fourth plus a fourth, and that's a half. No surprise there. The probability that I get a 1 or a heads is also a half by summing over the y's. The probabilities for Dr. U, so this is p sub capital Y of 0, and once again it sums to a half, and p sub capital Y of 1 once again sums to a half. So the marginal probabilities are the probabilities for the individual variables. So in summary, probability is very useful, applies to the study of random phenomena, and we'll see more properties as we go through the course. But probability is not enough for the study of big data. Probability is all about averages, and averages are all single scale. Big data, on the other hand, is often multi-scaled.